All right, so if you're watching this on a recorded video, I'm starting about 5 minutes late. I apologize for that. We were just talking about the fact that electromagnetic radiation is a type of energy that we call radiant energy, and it's called radiant energy because it's energy that radiates through space away from a source. And it may be radiating away from a source because that's where it's originated. Like, for example, you might have a fire. A fire is emitting visible light, and it's also emitting what we call infrared radiation, which is a type of heat. But EMR can also radiate away from an object because it's been reflected off of the object. So these are the 7 main classifications of EMR. And the order is important. So you need to know this order. And what you can do to begin with is at the top of your list where it says radio waves, is radio waves at the top? You can make a note that radio waves compared to the other forms of radiation don't have a lot of energy. And as you go down this list, things get more energetic. So microwave and radar EMR has more energy than radio waves. Infrared has even more energy, etc. So I'm just going to communicate that idea to you up here by writing the word energy at the top and writing the word energy at the bottom. But I'm just writing it larger at the bottom. You want to take what I'm saying here about the amount of energy with, as the saying goes, a grain of salt. You don't want to just take it as an absolute truth. Because if I tell you that X-ray radiation has more energy than visible light, in a general sense that's true. But if I had a 1,000,000-watt visible light laser, I can easily get more energy out of that than a dental X-ray machine, right? So I'm just talking, I don't know how you would even measure this, but if you had a certain amount of X-ray radiation in front of you, which is a ludicrous idea because it moves at the speed of light. You can't trap it. But if you had a certain amount of X-ray radiation and you had a certain amount of visible light radiation, the X-ray radiation would have more energy. Okay? So you do need to know the order of these, and I think by the time we're done with this lesson, you will understand how we can figure that out. Whatever all this stuff is, it's the same kind of stuff. We're not going to get into the specific theories about what EMR is today. I'll talk generally about it for a minute. But whatever light is made of, it's the same stuff that gamma rays are made of. And it's the same stuff that radio waves are made of. By the way, I hope you notice that sound waves are not on this list, because sound is not a type of electromagnetic radiation. Sound is a type of what we call a mechanical wave. There are 2 main theories that describe or try to explain what light is or what EMR is. So if you had a laser light, one of the theories says that what is in that laser beam is actually a wave. And there's a lot of evidence to suggest that light is a wave. All the things that water waves do and that sound waves do, or that any mechanical wave does, and I'm going to go back to physics 20 for a second in your mind and remind you that a mechanical wave is a wave where something physical is bouncing around or oscillating. Could be a slinky wave, it could be a wave on a string, it could be a jello wave. A sound wave has air moving around like the baffles in an accordion. Water wave has the water kind of sloshing up and down and the energy moves through it. What I'm telling you is that every property that those waves have, light does the same stuff. So I don't know how much of physics 20 is really memorable to you, but in physics 20 you studied something called refraction of waves. And when waves refract, they go from one medium to another, and they do things like they slow down or they speed up or they change direction. Is this at all vaguely familiar in your head? Maybe not the details of it, but you remember that when a wave enters a different medium, it undergoes changes. Well, when light enters a different medium, it undergoes changes. So light refracts, which means light behaves like a wave. Okay. On the other hand, There are also theories that we need to explain the behavior of light when it does other things. Light does other things that waves can't do. And I can't really mention them to you. I can mention them to you, but it's wasted breath. I can say, well, waves don't experience something called the photoelectric effect, but that doesn't mean anything to you. We're going to be learning about two main phenomena in this unit, the photoelectric effect and the Compton effect, where if you try to explain what's going on when light does this, and you say, well, light is a wave, you will not be successful in explaining what's happening. You have to assume to explain those other things that light is a particle. And this is a very, very strange thing about light, because we've kind of been taught in science up until about 1920 that things that carry energy can either be particles or waves. And I'll give you a perfect illustration. Cars are not waves, because waves can pass through each other. Waves can interfere and pass through each other. I know you might remember this if you were in my Physics 20 class, so I'll ask that first. Remember I showed you the video of the springs where the two waves went through each other? I'll show it to you again in this unit when we talk about interference of light, but in Physics 20 you're taught that waves pass through each other. Cars do not pass through each other, right? That's why we need insurance. Okay? Cars don't pass through each other, so cars behave like particles. They don't behave like waves. And sometimes we need light to be thought of as a particle. Now, if you just look at the front page of your handout, and you look at the picture or the drawing on the right-hand side, what does it say? Light is a what? It says both, doesn't it? If you just look at the broad outline of all of those letters, they form a W, an A, a V, and an E. But when you look at how all of those letters are composed, the W actually has a P and an A and an R in it. So this is what we call wave-particle duality, and this will start to get more and more interesting as we get deeper into the unit. Now let's start talking about these types of EMR. So all of these types of electromagnetic radiation together are referred to as the electromagnetic spectrum. And the only reason I'm showing this to you right now for one reason. If you were to go to page 637 of your textbook, you would see this diagram, and you would see a lot more information, but I've clipped it from this view. The thing I want to impress on you is we have the low energy radiation on the left going to the high energy radiation, but there's a lot of overlap. So that's the first thing I need you to appreciate is you might have radiation that if you called it ultraviolet and I called it X-ray, we would both technically be correct. There's this overlap here where very high energy ultraviolet radiation is pretty much the same as very low energy X-ray radiation. And that's pretty much the case everywhere except for when you talk about infrared, visible, and ultraviolet. It's very well defined because it's not like you can see some ultraviolet. You can't see ultraviolet. You can't see infrared. If you could, it would be part of the visible light spectrum. All right, so we're going to start off with radio waves. How are radio waves produced? They are produced in a very specific way. In a linear antenna, a piece of metal, electrons are forced back and forth. And I would rather not get into the precise details of what's going on, so you don't need to write this down because we will learn those precise details later. But when you have the electrons bouncing around in the linear antenna that's broadcasting the radio waves, they're going to produce magnetic fields because a moving charge produces a magnetic field. So what happens is you have this antenna where the electrons in it are moving back and forth due to a changing voltage or some device that's connected to the antenna. And then over here, I'll pretend it's 1984 again. I have my boom box listening to some Def Leppard, and on it there's an antenna. And this oscillation of electrons produces radio waves that travel out through space. And when those radio waves hit my antenna, guess what they cause to happen? They cause the electrons in the antenna to do the exact same thing that the electrons in the transmitter was doing. And then some magic happens inside to turn that electron motion into sound. Okay, we don't need to worry about that. But as a result, the radio waves travel outward in all directions. They hit this antenna and cause the electrons in the antenna to bounce around. In principle, when I connected those two handheld generators together and I turned one and the other one turned, that's exactly what's going on here, except there's no wire connecting these two things. It's happening in space somehow, and we will talk about that on Monday. But that's exactly what's going on. You have, I guess, kind of a generator effect going on here. Kind of. It's not really a generator effect. You're just creating magnetic fields by moving electrons. Because remember, a magnetic field is created if you have a charge in motion. That magnetic field travels out in space and does something else, which we'll talk about Monday, and eventually it hits here, causing these electrons to move. One of the things that's going to be important later is that means that if these electrons are bouncing back and forth, I will say 10 to the 8 times per second, the electrons in my antenna have to be going back and forth at the same rate. I don't know if you recall, but when I turned the hand crank on that little handheld generator, if I just went back and forth, back and forth, back and forth, the other handle would mimic that exact motion. So if I were to go back and forth more frequently with a higher frequency, then that other handle would go back and forth with a higher frequency. Okay? The frequency of the wave, the frequency of the electrons that are influenced by the wave, it's the same as the frequency of the source that produces the wave. So that's one thing you need to know about radio waves. Clearly they're used for communication, okay? I mean, radio, this is not satellite radio, by the way. I'm talking about old school AM, FM radio. And vehicles still have AM and FM radios. I don't actually personally know anybody who listens to AM anymore. There might be a talk radio show or something they're interested in, but AM is kind of not a very well-used band. But it's used for communication, radio waves. So as I said, satellite radio is not what I'm talking about here. Satellite radio is actually microwave radiation. But we'll talk about that in a minute. The wavelength. So this is that thing that I was talking about. It's hard for me to now switch gears and talk about waves, because if I'm talking about a water wave, I can say it's the water that's waving. If I talk about a sound wave, I can say it's the air that's waving. Whatever is waving in radio waves can have wavelengths from a meter up to 10 meters, up to 100 meters, 1,000, 100,000, technically 1,000,000, but if we had a radio wave of wavelength 1 million meters, I don't know that it's ever used. I don't know that there's an application for that. So whatever is waving, and we can't answer that today. It's not water, it's not air, but whatever is waving, when it goes from a high point down to a low point and then back up to the high point, like a transverse wave, the distance between those two crests is what we're talking about here. So whatever is waving, if it looks like this, the wavelength, lambda is the symbol we use for wavelength. I hope you remember that goofy symbol from last year, or Physics 20. That's what we're talking about. from crest to crest or trough to trough. Microwaves and radar. Microwaves and radar are produced in a very specific way that's similar to how radio waves are produced. They're produced by electrons. I want to say this before you see it and start writing it furiously. They're produced by electrons that are forced in a circular orbit. Okay, so if you crack open a microwave, what you will discover is something called a magnetron, which is a set of magnets, and an electron gun inside of it. And when those electrons are fired into that magnetic field, they move in a circular arc. That was an exam question yesterday. Due to the unbalanced magnetic force. Because if the magnetic force were balanced, the electrons would just go straight. And when those electrons move in a circle, they produce microwave radiation. So it's produced by electrons that are trapped in circular orbits due to a magnetic field. The magnetic field is not called a magnetron. A magnetron is the technology that we have that has this tiny electron gun in it along with a set of magnets. What are microwaves and radar? There's really, physically, there's no difference between microwave radiation and radar radiation. Okay. These are used primarily for communication. Okay. Different kind of communication than radio waves. Your cell phone uses microwave radiation. Well, I mean, I want you to understand when you're listening to somebody talk on your phone, that's a sound wave that your phone produces. That's not microwave radiation. I'm saying when you speak into your phone and that signal goes through space to somebody else's phone, or first to a cell tower and then somebody else's phone, or it goes to a satellite and then back down to a phone, that's microwave radiation. Or radar radiation. There's really, again, there's not much of a difference between the two. The whole concept of using microwaves to heat food was actually discovered in World War I when people would be, there wasn't a lot of money during World War I. A lot of the countries, particularly in the States, where this is what the story revolves around, a lot of the countries didn't have any money because they were putting all the money into the war effort. So when they were working in factories making things, they didn't have a lot of money for heating, and the workers would be usually cold. And they discovered in a radar factory that if they stood around the radar technology while it was on, their hands warmed up. While they were inside of a microwave oven. I mean, not literally, but that's where the concept of using it to heat food comes from. If you have a wireless router at home, it's using microwave radiation. If you have a garage door opener, it's probably using microwave radiation. I don't know if you've ever discovered this, and I learned this not that long ago, maybe 5-6 years ago. I was living on an acreage just outside of Millet, and there were certain times where our internet was just dead. Like, we had a signal at the modem coming in, and we had a signal going to the router, but the router wasn't able to pass the packets along to any of the other devices in the home. And it was that happened whenever somebody was using the microwave oven. If the microwave oven was on, it was interfering, and it was destroying the signal, basically. And then we realized you could change the frequency and the band on the router to get a better result. All of these little details that I talk about to try to pique your interest in this, but also because you might be mentioned, some of these things might be mentioned on exams, might be more familiar to you. The wavelength. Now, I know the wavelength of microwaves, and I haven't looked at my notes since the last time I taught this. It's like centimeters and millimeter range, and there's a way that I know that. So the wavelength range from millimeters to centimeters. And what I'm going to tell you is one of these things that, as a teacher, I'm lying to you. What I'm telling you is not strictly speaking true, but it makes sense and it helps you remember something. And even if you go through life having this misconception and you think it's true, it's not going to affect anything. When you look at the door to a microwave oven, there's obviously glass or plastic that you can see through, but there's a metal screen in there. I don't know if you've ever looked at one closely. I don't have one in here. There's a metal screen with holes in it. And it's an interesting question why the metal screen is there. And the metal screen is there to keep the microwaves from going through the door to your eyes and to you. And it's there to get the microwaves to be in the oven interacting with the food to heat it up. Does that make sense? That's why we need that metal there. And then one year, a student said, well, how come there's holes in it? And it took me just a little bit to figure it out. How many of you know why there's holes in it?
Well, I'm guessing it's because the waves are too big the wavelength of the waves is too big to actually.
Yeah, and that's the misconception, but it's going to work. So those holes, and I'll get back to my other question in a second, those holes are like half a centimeter, a few millimeters big. And since the microwaves can't get through the holes, that means the microwaves are slightly longer than the holes. It's not exactly what's going on, but it will help. Because whenever you see now what's the wavelength of microwaves, you should picture this door and go, oh yeah, it's a few millimeters or a centimeter. But why are the holes even there? Because if the whole purpose of the screen is to keep the microwaves out, why not just have a solid screen? It's got nothing to do, well, it's got kind of something to do with physics, so you can see in, right? And this brings up an interesting idea that if you can see in, the visible light that's coming off of the food, because it's reflecting from a light bulb off of the food to your eyes, the visible light can make it through the holes, which means the wavelength of visible light must be smaller than a millimeter. And yeah, it's a curious thing because we're caught in a physics trap right now. You go, well, why would the holes be there? Well, it's just so you can see it, so you can see what's going on inside. Now, infrared radiation, visible light radiation, and ultraviolet radiation are, I would go so far as to say that these three types of radiation are one type of radiation, but right in the middle of it is this range of wavelengths that we happen to see. So when we invented this classification system, rather than saying, oh, we've got this type of radiation, we've got the type we can see in the middle, and the type over here, which is called infrared, and the type over here, which is called visible. Which is called ultraviolet. Which of those three has the most energy? Evan, do you know? Ultraviolet. And then, which has the least energy, infrared. Visible light's trapped in between. So they're all produced in the same way. What I told you before about electrons in atoms going from a higher to a lower energy level to produce visible light is exactly how infrared radiation is produced and ultraviolet. So when I'm sitting around the campfire at the cabin in the summer and I see all these colors and visible light coming off of the fire, what's happening is chemical energy is causing atoms to bounce around faster, knock into each other, and in that collision, the electrons in the atoms get kicked up to higher energy levels. And those collisions are happening all the time. But even though the collisions are happening all the time, not every atom can be hammered all the time. So whenever an atom gets a little reprieve, it's no longer being interacted with by other atoms hitting it, the electrons in that atom go back down, just like a ball would roll downhill. But in the process, when a ball rolls downhill, we see kinetic energy produced. When an electron, quote, rolls downhill, you see visible light energy produced. And I want to impress on you something for Unit 4. If this is an energy level diagram for an atom, I know in chemistry, do you draw circles for the orbitals in chemistry? We tend to just in physics draw a line and say this is the energy, this is the energy. If an electron goes from this energy level to a lower energy level, we might produce infrared radiation. Okay? Now, does visible light have more energy than infrared? And you might have to look at your table because this is all new to you. Does visible light have more energy? That means, I'll do this again, infrared from that energy level to that energy level. If the electron's here, if it's going to produce visible light, it has to lose more energy. So it might fall 2 levels to produce visible light. Now be careful here. This is just a model. It could be that in a particular atom, this is still infrared, and maybe it has to fall even further to produce visible light. So once again, a little energy drop might be infrared radiation. A bigger energy drop might be visible light. An even larger energy drop might be ultraviolet. And by the way, there's more than 4 energy levels in an atom. There's lots. Okay? Somebody asks, well, the next one is X-rays, so can it fall so far to produce X-rays? No. None of the atoms in our universe have energy levels that far apart that would produce X-ray radiation. So, let's talk about the specifics. What is infrared radiation? It's heat. It's what we call radiant heat. If I were to touch something hot, not really hot, but my cup of tea, the cup is, I can hold it, it's not hot, but I can feel the warmth, right? I'm making physical contact with that cup. So heat is being transferred from the cup to my hand, but it's not radiant, it's conductive heat. The atoms in the cup are moving faster, they're bouncing and hitting the atoms in my hand, causing them to move faster, and that produces the sensation in my nerves of heat. That's not what we're talking about. We're talking about if I were to put my hands close to the cup, I can feel some warmth coming off of it. So there is something leaving the cup that's not atoms, it's energy that's eventually hitting me. When you're sitting around a campfire, you don't have to touch the flames to feel the warmth, do you? The warmth travels through space. So it's radiant heat. It's used for keeping food warm. I don't even know if they have buffets anymore, but you know, if you had a buffet, like you go to some place called Buffet World, they have those big orange lights. Do you know what I'm referring to? Kind of orangey. They're producing a little bit of visible light in the orange range, but if you put your hands close to them, man, they're warm. I guess you use infrared heaters in restaurants too, right? In the kitchen and to keep things warm. Does anybody work in a restaurant? No? Okay. Certain types of night vision. I won't get into the different types of night vision, but some night vision goggles don't use infrared radiation. They just use whatever little bit of visible light is present, they amplify it. What a true infrared night vision camera or goggle set would use is it would pick up the infrared radiation coming off of the objects. It picks it up on a photosensitive cell that's sensitive to infrared radiation, and it turns into a visible image on a computer screen. Okay? And as I said, some animals, pit vipers, I've lost the picture, but I had a great picture of a pit viper, which is a type of snake. And when you look at the head, you see these 2 huge black eyes. And then you realize those are not the eyes. The eyes are these little tiny, tiny things above those black spots. Those black spots are pits. They're kind of concave impressions in the skull of the snake. And it's coated with a sensitive tissue that can detect infrared radiation. So I don't know what that would be like. It's hard to wrap our heads around what it would be like to see infrared. But if it's pitch dark and there's a mouse moving by, the snake will still be able to detect that there's a mouse moving by. Okay. What are the wavelengths? Longer than 700. I want to really highlight that first. Longer than 700 meters. Nanometers. Up to millimeters. Now, I've talked about nanometers a couple times. By the way, when we get up to millimeters, now we're into the microwave range. That's why it's up to millimeters. If you go to your formula sheet and look up nano, I don't have it there. There it is. There's nano as a metric prefix. It's 10 to the negative 9. So when I say up to 700 or from 700 nanometers, what is that? 700 nanometers is 700 times 10 to the negative 9 meters. And you could just enter that in your calculator. In fact, I'd like you to do that. Just go 700 times 10 to the negative 9 and hit enter. And you'll discover in standard scientific notation it's 7.00 times 10 to the negative 7. Why does it become negative 7? Because 700 is 7 times 10 to the 2. And when you multiply 10 to the 2 by 10 to the negative 9, you can add the exponents and you get negative 7. The only reason I'm mentioning this now is, well, twofold, so that you know what nano means, but also when you see standard scientific notation that's times 10 to the negative 7, which is very common, it's hundreds of nanometers. Okay? We deal with hundreds of nanometers quite frequently. So that's infrared. Visible, well, I think it's obviously the type of radiation that we can detect, that we can visually detect. We can detect infrared with our skin, right? Because infrared is radiant heat. But visible light is the type of radiation that we have evolved to detect visually. Which just, you don't want to think about the way the world works too much. You go a little crazy. But to me, that's amazing. That the image that you have in your brain, because the image you're seeing is something in your brain, is formed because light reflects off of me, exposing all the details in the image. That light hits the back of your eyeball, and your brain waves its magic wand, and you create this image in your brain. That's pretty amazing. We cannot do that with any other type of radiation. You can feel, we can sense infrared, but you can't see it. You can't get an image of it. Wavelengths are from about 400 nanometers to 700 nanometers. I didn't use the most vibrant colors up here, but I hope you can see that the 400 is a purpley color and the 700 is red. When you talk about the visible light spectrum, they still teach you that, Roy G. Biv? Red, orange, yellow, green, blue, indigo, violet, the 7 colors. 400 nanometers is the violet end. So violet has a short wavelength. Just a second here. I guess I need to talk about this, and I want to talk about frequency right now. And I'm going to actually go back here and add something to this. I told you, and I won't add it just yet, but I told you that in this list, radio waves have little energy and gamma rays have more energy, right? You with me? Now, I want to take a little break from this and talk about water waves. If I were sitting, and this is the analogy I always use, so if you were in my physics 20 class, you've heard it, but I were sitting with my feet hanging over the dock at a lake, and my foot is just almost touching the water, and I'm listening to some Moody Blues. It's an old band from the 70s. And my foot is kind of dipping in and out of the water very lazily, like 1 time per second. I'm going to create a water wave that travels away from my foot. And what happens is you get this picture, you get this idea in your head that what happens is you get a wave that looks like this. And the distance between these two is the wavelength, of course. Now, what determines the wavelength? Well, in an indirect way, I determine the wavelength because the reason there's a distance between the peaks is that's a distance that's there because my foot wasn't disturbing the water at that point. I smack my foot into the water, I create a ripple that travels away from me. And then my foot goes in again, and there's another ripple that's created behind it. So the longer I wait between toe taps, the greater the wavelength will be. Are you with me on that? Does that make sense to you? So Now I switch gears. It's a different time of the day. I've finally woken up, and I put my headphones in and I listen to my favorite German thrash metal band. And my foot's going in and out of the water like 20 times a second. Those ripples are going to be really close together, aren't they? Because I will make a ripple, and that ripple will not get a chance to move very far before I make another ripple. And the point I want to make to you is that the German thrash metal is more energetic. There's more energy involved in that action. And I get a smaller wavelength. And what that means is that when we look at this list, if you have a lot of energy, you have a tiny wavelength. But if you have little energy, you have a large wavelength. And we can also include frequency on here. Because when I was listening to the Moody Blues album, or almost said tape, when I was listening in my head to the Moody Blues track, the frequency that I was dipping my toe in and out of the water might have been 1 time per second. It was a very small frequency. And a small frequency produced a very large wavelength, which just meant the wave was very lazy. This long, loping movement of water. But when I was listening to the German thrash metal, I might have been dipping my toe or foot in and out of the water 20 times per second, which would mean the frequency would be 20 hertz. It's quite high. By the way, the frequency of this stuff is not like 20 hertz. It's big. It's huge. We'll learn about those numbers tomorrow. So why did I get on this? I got on this because we were looking at the colors violet to red in terms of wavelength. Let me go back to there. This is where I was. So which of those colors of light has more energy? Well, it has a smaller wavelength for violet, and if violet has a smaller wavelength, there must be more energy involved. So violet has more energy than red. Well, wait a minute. That totally makes sense because ultraviolet radiation in your list has more energy than infrared. So when we go infrared, visible, violet, we could go infrared, then red, all the other colors, then violet, then ultraviolet. In other words, the violet end of the visible light spectrum smashes into the ultraviolet spectrum, and the red end touches the infrared. Any questions so far? Ultraviolet. Okay, so ultraviolet is the first one in the list that is dangerous. It can cause cancer. Repeated exposure to ultraviolet radiation, which is produced by our sun, can cause skin cancer, which is why you should wear sunblock if you're out in the sun a lot. That sunblock literally stops the ultraviolet radiation from hitting your skin. Now, just because something can cause cancer doesn't mean, we should run around in a panic. You don't always wear sunblock. Repeated exposure can cause skin cancer. It's called ionizing radiation because ultraviolet radiation, unlike visible light or any of the upper ones in your list, ultraviolet radiation has enough energy that it can hit a molecule and pop the electron out of the molecule. And that's called ionizing something. So just to bring this into a chemistry kind of analogy, if you took a look at solid sodium metal and you took a look at chlorine gas, these two things are very, very dangerous, incredibly dangerous. Sodium metal is an explosive metal. You can find some great YouTube videos of people disposing of sodium metal by throwing them off a bridge into a river. When sodium comes into contact with water, it produces hydrogen gas and energy, and the energy ignites the hydrogen gas and it explodes. Chlorine gas is very noxious. If you were breathing chlorine gas, it would get into your vocal cords and your lungs, and it would dissolve in the water that's in there producing hydrochloric gas, or hydrochloric acid rather. It's very dangerous. But when you react those two things together, you produce, under the right conditions, sodium chloride, which is table salt, which you can sprinkle on your fries, and it tastes good, right? I mean, it adds something. And the difference here, I want to talk about the sodium between this and this. I don't know what state I want to call this. We won't worry about it. The difference between sodium and a sodium ion is 1 electron. A sodium ion is a sodium atom that an electron has been removed from. So the absence of 1 electron changes the total behavior of the atom or molecule. Now, what I'm about to show you, keep in mind, I am a physical science trained teacher. Okay, I have a degree in physical science. I didn't take any biology in university, so this is a oversimplification. And my oversimplification starts off by me drawing a DNA molecule. There's my DNA molecule, which obviously it's more complicated than that. And this is a perfectly healthy DNA molecule. It's the helix. And if I lose an electron, it doesn't become a DNA molecule anymore. It becomes a DNA ion. And your body doesn't react well to a DNA ion. This is a mutated DNA now. It's not normal. It's been damaged. And the thing about DNA is DNA makes exact copies of itself, right? You don't even need to take biology to know that. It's reproducing. So 1 becomes 2, becomes 4, becomes 8 over time, and next thing you know, you have a whole mass of tissue with crappy DNA, and that's a cancer cell or a cancer tumor. Now that is an oversimplification, but that's basically the idea. Ultraviolet has wavelengths less than 400 nanometers. It's hard to believe, I know, for some of you, that you will be successful in memorizing all of this, but you will. You're not the first group of students to take Physics 30 and be faced with this task. If we put these 3 types of radiation together, the infrared, the visible, and the ultraviolet, this is what it looks like. That we have infrared, which we can't see. We can kind of sense it a bit with our skin. It's warmth. And then all of a sudden, we get down to a wavelength of about 700 nanometers, or we get up to that energy, and you can start seeing this radiation. There's no difference between what is here and what is here. There's no difference at all, other than the fact that when this hits your eyeball just goes to sleep and says, I don't care. I'm not going to tell you about it. And as we get more and more energy, and then we get to here, and we move into the ultraviolet, your eyeball turns off again. Your eyeball is just not tuned like a radio station or a radio. It's not tuned to pick up that frequency or that wavelength. So if I was writing an exam and I saw that we had a wavelength of 300 nanometers, I know it's ultraviolet because I go through this thought process. It's outside of the range of 400 to 700. It's less wavelength than 400. So is that infrared or ultraviolet? Well, a small wavelength is a lot of energy. And I know ultraviolet has a lot of energy because it can cause damage. So all of that goes on in my head very rapidly. All right, some photos here. This is a photo taken with a visible light sensitive photocell. So it's a digital image. It was taken with a digital camera, and the photocell is sensitive to visible light. So it's been programmed so that any visible light that hits it is reproduced on a screen somewhere. It ignores infrared and it ignores ultraviolet. And that's our sun. This is, sorry, actually this one is infrared. I take that back. This must be infrared. It is infrared. Yeah, that's not visible. You wouldn't actually see something come out of the sun like that. This is a visible photograph, visible light photograph of the sun. So this was taken with just a photocell that's sensitive to visible light. Do you see the couple of dots or blemishes in the left-hand side there? It's actually the International Space Station and a space shuttle that happened to be passing in between the camera lens and the sun when the photo was taken. I don't know if I'll be able to make this much bigger. I mean, it's going to lose some clarity, of course. You can kind of make them out now. And then the final photograph I'm going to show you is one that was taken with a photocell that was sensitive to ultraviolet radiation. One thing I want to mention here is some people will look at this and go, okay, the infrared was orange, the ultraviolet is purple. Does that mean infrared radiation is orange? No. It means that somebody has decided to color the information orange so that we could see it, and color the information violet so that we could see it. Bottom line, in the end, there's a lot of action going on in the sun. Electrons are going up and down all the time through various different distances, producing these three types of EMR. We have two more left. X-rays you're probably most familiar with other than visible light. They're ionizing radiation as well. I mean, heck, if ultraviolet radiation can knock electrons out of DNA, then X-ray radiation sure can, because it has more energy. X-ray radiation is produced in a very specific way. Electrons are accelerated to a high speed, and they're stopped by a metal target. I'll get back to that. I guess we'll do this first. Used primarily for medical and dental diagnoses. And an average kind of wavelength for X-rays is about 10 to the negative 10 meters. You should maybe make a note that 10 to the negative 10 meters is a tenth of a nanometer. Which would mean, even though I didn't tell you this, something that's 10 nanometers would still be ultraviolet. It's only when we get down to less than a nanometer that we would call it X-ray. Let me explain to you how I remember this, and this is just something I came up with, and I don't know why. Maybe I have too much time on my hands. As a student, I needed a way to remember that it was 10 to the negative 10 for X-rays. And as we're all familiar, memorizing stuff is not always easy. Well, it isn't for me. So when I was growing up, in the back of comics, you could buy all this stuff. Sea monkeys that you would sprinkle these in water, and then there would be these little magical sea monkeys floating around. One of the things you could buy would be X-ray specs. Have you ever heard of these? Yeah, they don't work. They don't do anything. Okay, they just look stupid. But you'd buy them for $1, and they'd make everything look blurry. But when you take a look at a pair of eyeglasses, there's a 10 to the negative 10 in there. You can take those 3 straight lines and those 2 circles and make 10 to the negative 10. There's a line and a circle. There's a line and a circle. So you can reform the shape of X-ray specs into 10 to the negative 10. I know that's really dumb. I'm almost embarrassed to describe that to you. But I also know that some of you will remember it now. Okay? So it's produced by high-speed electrons that are suddenly slammed into a metal target. So we're almost done this little jaunt through an introduction to electromagnetic radiation. I want to review some things, though. I want to talk right now just for a minute about how all of these are produced. And I remember all this because I've taught it for a very long time, like 30 years. When you look at radio waves, they're produced by electrons that are accelerated up and down in an antenna. And in order they're accelerated because if an electron is going to move up then down, it's got to stop and then speed up. So radio waves are produced by accelerating electrons in a linear antenna. Microwaves and radar are produced by electrons being forced into a circular orbit by an unbalanced magnetic force. And that's a centripetal acceleration. We're accelerating electrons. When you look at infrared, visible, and ultraviolet, they all involve electrons losing energy in an atom, falling to a lower energy level. And losing energy is kind of like acceleration, but it's not exactly. But it's kind of like acceleration. When you look at X-ray radiation produced by high-speed electrons suddenly stopped. So they experience a negative acceleration when they hit a metal target. So each of these 6 forms of EMR all involve electrons, but the last one doesn't. So the last one is very unique. I guess I'll show you some X-rays first. This is Wilhelm Röntgen was a German amateur physicist and photographer, or physicist and amateur photographer, I guess I should say. He was a scientist who liked to dabble with photography, and back then, obviously, they didn't have digital cameras. They had film, and the basic idea behind a film camera, at least back then, was you had a piece of film which was sensitive to visible light, and you had it covered up. Otherwise, if you took it home from wherever you bought it, by the time you get there, it would be exposed to the visible light. So you have it covered up, and then you go, okay, smile, and you would uncover it and then cover it back up. And what happens is in that short period of time where the light is allowed to hit the film, where lots of light hits the film, it causes a different shade in the film than other places where little light hits. And that's how you create a photograph. Now, that's a negative. You have to create a positive from it, but I don't care about that. What he did was he had his film tucked away in a desk drawer in a box that light couldn't get into, and he would every day throw his keys onto that box when he went into the lab. And he discovered after doing some experiments with electrons that when he took a picture of something and he developed the picture looked great, but there was a shadow of his keys over top of it. So something was going through the box, but not the keys, and it was exposing the film. And that's what X-rays are. Anyway, when he figured this out, he went wild. He was taking X-ray photographs of everything. This is a photograph of his wife's hand. The first time I saw this, I was a little confused because that hand looks a little alien to me. But you need to understand that where your fingers start on your hand, that's here, right? Her fingers aren't these big, long things. Those are her wedding bands, obviously. And parts of matter that are very dense, like the bones, don't allow as much of the X-ray radiation through, so the film is darker there. A few other X-rays. Talking about this one because imagine prior to X-ray diagnoses that somebody was shot in the hand with a shotgun. Let's just say, this is just a single pellet from an air rifle. But if you were shot in the hand back in 1800 and whatever with a shotgun, first of all, the pellets were probably made of lead, which means you would immediately start getting lead poisoning. And the only way they could locate all of the pellets to get them out would be to dig around. Right? So they would most likely just amputate your hand, that would be my guess. But with an X-ray, you can actually see what the damage is. This is a broken tibia. What's the tibia? Is that the bottom of your leg? No? I'll just say, I think it's the bottom of your leg, your shin bone, I think. It's pretty obvious. I don't know what happened, but I know what the result was there. If you take a look at this, these are dislocated bones in the hand, so all of these bones, like this bone here where the red dot is, should actually be down where the other red dot is. So all of the bones have been rolled over. Dislocated bone in the foot, same kind of idea. And we move on to gamma rays. So gamma rays are the ones that are not produced because of behavior of electrons. They're produced through nuclear, I guess we'll do that first. They are cancer-causing because they are ionizing radiation. Basically, once you get to the energy of ultraviolet, then anything with even more energy can cause damage as well. Strangely enough, gamma radiation can cause cancer, but used in the right way can treat cancer. Throughout this course, there are so many connections between what we learn and what we have learned. You know you can create electricity by taking a generator and spinning it. We haven't really talked about how we actually create the electrical energy we use around us, but we use generators and we get them to spin. So how do we spin the generator? I suppose we could have 1 million people turning little handheld generators all at the same time. But what we do is we use other forms of energy to turn the turbine or generator. So a hydroelectric generator puts that turbine or generating apparatus out below a waterfall, basically. They dam a river up to build up lots of water, and then periodically they open the dam, the water goes rushing off, it hits that turbine and causes it to spin. Okay? You have probably heard of a coal-fired power plant. Well, what a coal-fired power plant does, essentially, is you burn the coal. There's a lot of chemical energy in coal. You burn the coal. You use the heat produced from that reaction to turn water into steam. You funnel the steam into a narrower and narrower and narrower pipe, and you point that pipe at a turbine. Basically, that's an oversimplification. A nuclear power plant, which would be what we're talking about here, because gamma rays are produced in nuclear reactions. A nuclear power plant allows a nuclear reaction to take place and does exactly what a coal power plant would do. It's just that there's more energy available in nuclear. This stuff can be used to kill certain types of cancer cells because literally there's so much energy that if you aim a beam of it at a tumor, it literally just obliterates that tumor. I don't know why cutting it out doesn't work, but this would. Very tiny wavelengths. All I would say to you is if X-ray is 10 to the negative 10, then 10 to the negative 11, 10 to the negative 12, 10 to the negative 13 would be gamma. Oops. So how are they produced? You know what, before you write that down, because I know you guys want to write it down, but how are gamma rays produced? They're produced by changes that happen in a nucleus of an atom, basically. And there's no electrons to be found in a nucleus. So things like fission and fusion and radioactive decay, any nuclear process is one in which you will produce or can produce gamma rays or gamma radiation. That went a little longer. I should have known it would go this long. I always try to make it a little bit shorter, but there's some things that we just need to talk about here, or I need to talk about. So that's it. That's a nice summary of everything that you need to know. I've told this to you before. I think you know this about me. I'm really not a big fan of writing to learn. That's why normally we don't take notes. But my experience tells me that writing this stuff down is what needs to happen in this area. You could go to your textbook in chapter 13. They have a nice diagram of the entire electromagnetic spectrum with wavelengths on it. And on the facing page, I believe they have everything that I've talked about. So you can also use that. So that's it for today. I'm going to hand back your exams, and you can use the last 5 minutes or so to take a look at them. And I apologize, we don't have more time.